This is the second segment of the 1.9 video, and we're going to continue on and do an exercise here. This exercise should be really easy. It's just all about notation in a way, and it's a question that we often ask on exams. So I do know sometimes students get thrown by it, and it's like, oh, this is so easy, don't mess up. So make sure you know how to do this, is what I'm trying to say. And so here we go. Sometimes our textbook gets lazy and writes a column vector, x1, x2, x3, x4, horizontally. This is just to save space in the book. There's no other reason for doing this at this point. So, and it happens in some of the exercises in this section. So this is how the textbook would write this exercise. Suppose that T below is a linear transformation from R4 to R3. And what we want to do is we want to show that T is a linear transformation here by finding a matrix that implements the mapping. So right now it's just a function. And how do we know it's a linear transformation? Well, if we can show it's equivalent to matrix multiplication, then any matrix multiplication transformation is a linear transformation. So this one must be. Okay, so now I'm going to just recopy parts of this. So what they're saying, T of x1, x2, x3, x4, I would write as this. So we're taking T of a 4-component vector, so a vector in R4, and we're saying the image of that would be a 1, 2, 3 component vector, where the first component is x1 plus x2, the second is x2 minus x3, and the third is 2x1 plus x3 minus 2x4. Now what we're doing to these variables seems very linear. We're just taking linear combinations of entries, so it seems like it's a linear transformation, but if we can find that matrix that defines it, then that will take care of this problem. So now how are we going to do this? So this is, again, this is an R4 vector, and the linear transformation takes us to R3. So we're looking for, we need a matrix A that is 3 by 4, right? 3 rows, 4 columns, because we would turn those dimensions around to get our matrix. Because the domain space is R4, I'm going to use the columns of I4, the 4 by 4 identity matrix, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. And we're going to call those E1, E2, E3, and E4 here, since we have 4 dimensions. And I'm going to compute T of each one of those. I'm going to compute T of E1. So T of 1, 0, 0, 0. And I just plug in because x1 is 1, x2 is 0, x3 is 0, x4 is 0. So I'm just going to plug in. So I get 1 plus 0, or 1, for the first entry. I get 0 minus 0 is 0 for the second entry. I get 2 times 1 plus 0 minus, so I get 2 there, 1, 0, 2. And I go down the line for each one of these. T of E2 is T of 0, 1, 0, 0. So now x2 is 1, and all the other x's are 0. So I get 0 plus 1 is 1. I get 1 minus 0 is 1. And I get 2 times 0 plus 0 minus 0. I get 0 for that third entry for T of E2. And T of E3, which is T of 0, 0, 1, 0. So now x3 is 1, and all the others are 0. So I get 0. I get 0 minus 1, negative 1, and I get 0 plus 1 minus 0 is 1. So there's the image of TE3, and we need one more. So the image of E4, where only x4 is 1, the other entries are 0, so we get 0, 0, minus 2. And so my matrix A is just going to have these columns. That's it. So 1, 0, 2, 1, 1, 0, 0, negative 1, 1, and 0, 0, negative 2. There it is. That's what we were trying to find. That's the standard matrix. That's a matrix that defines this linear transformation. And so therefore, since t of x is equal to a times x, t is a linear transformation. And if you want, we can just verify. That's all you got to do. But we can check ax, which is a times, it's going to be a x1, x2, x3, x4 component vector. That would be x1 times the first column, 1, 0, 2, plus x2 times the second column, 1, 1, 0, plus x3 times the third column, which is 0, negative 1, 1, and I gotta squeeze it in here, plus x4 times the fourth column, 0, 0, negative 2. And what is that actually going to give me? That's going to give me a vector, when I add all this up, in R3, x1 plus x2. And then my second entry, I get 0 plus x2 minus x3 plus 0, x2 minus x3. And then I get 2x1 plus 0 plus x3 minus 2x4. And notice that what I got here, I hope, matches up with what we started out with at the very beginning for this problem. So there was the exercise. And our solution is right here, and there's the matrix A. We just took the image of the E1 through E4 vectors as columns. And I'm going to stop this segment here because the next part is all, I want to keep it all together. It's going to be a little bit more involved.